Use an equal sign to represent equality, so each of these expressions are equal to one another. If we solve for the variable, we can see that x is going to have a value of 3. That means there is one solution. 3 is the only number that when we put it back here, the left side will equal the right side. If we have an inequality, we have either a greater than, less than, greater than or equal to, or less than or equal to symbol. And in this particular example, x can be any value greater than 3. If we choose any number larger than 3, it will be a solution to this inequality. So for example, if I choose, let's say, a 10, 10 plus 2 is 12, 12 is greater than 5. And we can represent those solutions on a number line. I'm using an open circle to show that the value of 3 is not included, but every value of x that is greater than 3 is going to be a part of that solution set. So to solve this inequality, I'm going to isolate x by dividing that 3 out of both sides. 3 divided by 3 leaves me with 1x, and then negative 12 divided by 3 is going to be negative 4. All values of x that are equal to negative 4 or less than negative 4 will satisfy this inequality, and then we can represent those on a number line. In this last one here, when I go to isolate x, I'm going to divide out that negative 2 coefficient. And remember that anytime we multiply or divide by a negative, this inequality is going to flip. And so our solution ends up becoming x is going to be greater than negative 5. And again, we can represent that on a number line. And then you can always test some values. So let's pick a value greater than negative 5 for x. Let's say that x is 0, which would be over here. If I substitute a 0 in, negative 2 times 0 is 0. 0 is less than 10. So that is a true inequality. We have the arrow going in the right direction. In this lesson, we're going to look at linear inequalities, and we're going to begin with linear inequalities that have one variable. So if we have only x equals or y equals, that tells us we're going to have either a horizontal or a vertical line. We know that any vertical line has an equation of x equals, and we're looking at where does that line cross the x-axis. So for example, if I cross where the x-intercept is 2, the equation for that line is x equals 2. If I have a horizontal line, I'm looking at where does that graph cross the y-axis. So if this is negative 2, the equation for this line is y equals negative 2. So x equals, I'm going to just use a variable to represent any value that we could put in there, depending on where we cross that axis. And then y equals, I'm just going to put a variable in there to indicate where we're crossing that y-axis at. Each of these equations is an equality. We have an equal sign. If we replace these equal signs with one of these 4 signs, we now have an inequality. A linear inequality in one variable can be drawn on a number line, like we looked at previously as a review from what we did in earlier years, or we can also draw it on the Cartesian plane. They will appear as either vertical or horizontal lines. A solid line is now going to replace that closed circle. It's going to show that all points on that line are going to be included in the solution. A dashed line is going to replace that open circle. All points on that line are not going to be included in the solution. We're then going to shade the region of the graph that contains our solution set. If we have, for example, x is less than a, that means all points in this region are going to have an x-coordinate that is less than, for example, 2. If we have x is greater than a, we're going to shade to the right to show that all points in this region have an x-coordinate that is now greater than our a value, which in this case is 2. If we have a horizontal line and we have y is less than this value, we're going to shade below to show that all points in this region have a y-coordinate less than that value. And if we have y is greater than that value, we're going to shade above. All y-coordinates in this region will have a y value greater than negative 2. So when we go to graph either a horizontal or vertical inequality, we first want to take a look and say, okay, is it vertical or horizontal? So we can see that x in this case is going to be a vertical line. It's passing through the x-axis at 4. And because we're not including that point on our graph, we're going to use a dashed line. And we're shading all points that are going to have an x-coordinate greater than 4. So this region over here is what we're shading. y is less than -1. So y is a horizontal line crossing the y-axis at -1. We're not including any points on that line. We don't have that equal sign there. So we're going to shade below. Every point in this region will have a y-coordinate that is less than -1. And in this particular one, we are going to include all points on that line that have an x-coordinate of 2. So we're using a solid line now, and every point in this region will have an x-coordinate that is less than 2. Every point on that line will have an x-coordinate that is equal to 2. Horizontal and vertical lines are special cases. Most of the time you're going to see a linear equation written in 2 variables, and I can see that this is already in slope-intercept form. So I know my y-intercept is 3. I know that I have a slope of 2. That allows us to get this line drawn, and because we have y is less than this, we are going to use that dashed line. We're not including any value on that line as part of our solution. Y is less than, so we are going to be shading the region below that boundary line. Our solution will include all values in that shaded region. We can then choose points in either the shaded region or the non-shaded region in order to verify whether or not we've shaded correctly. 0, 0, the origin, is the easiest point to work with. So I can see that in this particular graph, this is in the shaded region, which means it should be in the solution set. So if I substitute 0 in the place of x and 0 in the place of y, I should have an inequality that is accurate. So let's choose that point. We're going to substitute into this inequality, and we can see that we end up with 0 is less than 3. That is a true statement. Therefore, that point, 0, 0, in this particular graph is included in the shaded region, and it represents all other points. So if we were to choose any point within here, substitute in the x and the y coordinate, we will have an inequality that is true. If we choose a point in the unshaded region, so for example, let's maybe choose, this is a point of -5, 0. I'm going to substitute in, so my y-coordinate is 0, my x-coordinate is -5, and when we work out this inequality, we end up with 0 is less than -7. That is not a true statement, therefore any point within that region is not going to be part of the solution set. If you happen to choose a point on this line, so for example, I know that I have a y-intercept at 3, so this point is going to be 0, 3, and I substitute that in, I'm going to end up, my y-coordinate is 3, my x-coordinate is 0. I end up with 3 is less than 3. That's not a true statement, and so because we have this dashed line here, we know that any point on that line will not satisfy that inequality and will not be part of that solution. Let's try another one here. So again, I can see that I have a linear equation in 2 variables. I first want to get it into y equals form so that I can easily graph it. So let's divide out that coefficient of 2 from each side. And when I do that, 6x divided by 2 is 3x, -4 divided by 2 is -2. So now I can go ahead and plot that y-intercept of -2 and use the slope to get that line. We have y is greater than this expression, so it's not equal to. We're using a dashed line, that's going to create our boundary, and we're shading all values of y that are greater than this. So we're shading above that line, and then we can quickly test this. So I would take the origin because it's easy to work with, 0, 0. In this case, it is within that shaded region. So if I put a 0 here, and that's going to be 0, I end up with 0 minus 2 is -2. 0 is greater than -2. That is a true inequality. Therefore, this shaded region contains the origin. I've shaded the correct side. And then in our last one, when we go to isolate y, we end up dividing out that -3. So remember, you have to flip that inequality. Because we are including every point along that line, we're going to have a solid line. Y is less than or equal to all of this. So we're going to shade all y coordinates below that line. And then this is where you might want to test just to make sure you have shaded correctly. So the origin here is not in that shaded region. Therefore, it should not be a solution. So when I substitute that in, I'm going to go back to the original. If I put a 0 here, that term's gone. I put a 0 here, that term's gone. So we're left with 0 is greater than or equal to 6. That is not a true statement. Therefore, this should be be in the unshaded region, which it is. So you know you've done it correctly. If I choose a point on that line, so let's say we have a point of 0, -2. If I put in 0 for x, that term's gone. If I put in -2 times -3, I get 6. 6 is equal to 6. Therefore, every point along that line is part of our solution set. And then if you're given a graph and have to determine the inequality that represents that graph, the first thing we want to do is get the equation of that line. I can see it's a linear graph. So if I can start in slope-intercept form, I can see that I have a y-intercept of -2. And then if we choose another point on that line, we can see that we're going down 2 over 1, down 2 over 1. So I know my slope is going to be -2. So then if you take a look at the graph, we can see that we're shading above, and we also have a solid line here. So this is going to be greater than or equal to that -2x minus 2. And then you can always test. So if I take the origin, I can see the origin is in the shaded region. So when I substitute that back into this inequality, I end up with 0 is greater than or equal to -2. That is a true statement. Therefore, that origin should be in the shaded region, which it is. So we know we've got the correct inequality.